Hi, everybody. So, we're resuming after a little bit of a hiatus, the category theory crash course with the topic of adjoint functors. So, again, this is a really big topic that really starts bringing together a lot of the previous lectures. So, it generalizes things like universal properties, representable functors, sorry, and etc. So it kind of synthesizes a lot of these topics. So we'll give a kind of overview of the idea. We'll give the definition, a couple of the core kind of canonical first examples, a couple breadcrumbs to some more cool ones, and then finish with a big theorem called the adjoint functor theorem. So I came across, a fun slogan from the famous book, Categories for the Working Mathematician by McLean. But the idea is, he says, the slogan is adjoint functors arise everywhere. I can't write, sorry. He's pretty bold with some of his things. Some of the things that come up later, like con extensions in his book, I think he says like all concepts are con extensions, which is pretty cool. But that's the kind of the flavor of category theory. You generalize and generalize until everything is within your sights. All right. So enough waffling around. Let's give the definition. So let's say C and D be two categories. And suppose we have two functors. So I've got functor f from C to D and a functor, say G, from D to C. So this always occurs in pairs. So we say f is left adjoint to, let me make that clear, left adjoint to G, or you can also say G is right adjoint to F. Or they form an adjoint pair if the following condition happens. So if for all x in the category C and y in the category D, there exists a natural bijection of Hom sets between the categories. So what we say is the set of homomorphisms in the category D from f of x to y is in bijection with a set of homomorphisms in C from x to f of y. This is our main definition here. This natural bijection. So the naturality here is really important. So think about natural from the natural transformations of functors kind of thing. So this is sort of like a functorial bijection of sets. So the data of this natural bijection for each choice of x and y is sort of like a family of universal properties. Or like a family of universal morphisms between these types of objects. And one way I like to think about this is in terms of, let's say, like kind of solving problems. So maybe I had a problem where the following. So let's say I have a given set. So let S be a set. And I want to say, what is the most efficient way to turn S into a group? Into a group. Let's say maybe a group G. And not only that, I also maybe would like these things be related in a way like maybe that there should exist some canonical morphism, set theoretic map from S into G. Right, we don't want to just kind of like randomly associate something. They should be related in some way. So this is a classic problem that is solved by adjoint functors. And so maybe if you're familiar with this problem, this is the notion of a free group on a set. The solution is we take G to be, I'll call f of S, the free group on S. So this is the most universal way of turning the set S into a group. Another way of thinking about this is the following. So I'll give it in terms of the Hom sets in just a second, but I want to think about it like this at first. So given any group, or the category of groups, so I have some group, maybe little g, I can forget the fact that it is a group, and thus I obtain a functor to the category of sets. Right? So we just send it to, I'll write like bars around G to say underlying set. Of G. So maybe right is U of G. I'm going to think about this as like a functor. The question is, what this free group thing does is it gives us actually an adjoint backwards. It gives us a functor going the other direction from sets back into groups. So the free group construction being the most efficient way to turn a set into a group is the same thing as saying that these two things form an adjoint pair. So sometimes when I have like F is left adjoint to G in this way, we write like, use this symbol to denote that relationship. Which one is on the left, which one is on the right. So in this case, the way I've set things up, the free group is the left adjoint to this functor U. Here. So said differently, I have a natural isomorphism in the category of sets between, let's say, f of S for any set S. I put any group G here. And I have a bijection with the set of homomorphisms, set functions from S to the underlying set of G. Right as U of G. So I'm not going to go into too much detail about, the whole construction on free groups. I'm assuming if you guys have seen some group theory classes and some abstract algebra, you're familiar with the idea of a free group. Or maybe a free abelian group or a free vector space. The construction is very similar. This is such a ubiquitous setup that it's often called a free forgetful adjunction. Free forgetful. Pops up all the time, where you could have things like you have, say you have an abelian group and you have a forgetful functor to the category of groups. Right? You can go from category of abelian groups and forget that you are an abelian group, you're just a group. This defines a functor, and you could ask, does this thing have an adjoint? Is there a universal way of taking a group and turning it into an abelian group? Yeah. You mod out by the commutator subgroup. So there's an adjoint pair there. You could take a ring, right? Say you have any kind of commutative ring. You could forget the fact that it's a ring and that it just has an abelian group underlying structure. So the question is, what's the most efficient way of turning an abelian group into a ring? And you take a group ring. There are a lot of different kind of pairs like this. So this ubiquitous kind of relationship is called a free forgetful adjunction. Here. You can think about this Hom-set definition here. What this is really saying is very familiar to anyone who's taken a linear algebra class. So we'll take a quick sec from dealing with groups to think about, say, real vector spaces. So similar idea here. In the following. Say, if I have two vector spaces, V and W, are two vector spaces, say over the reals or pick your favorite field, doesn't matter. Vector spaces. Let's say S is a basis for V. And let's say L is a linear map. Say R linear in this case, or whatever your field is. Linear map. Then L is completely determined by its values on the basis S. Uniquely determined by its values on S. This is the exact same idea here. In this case, for this category down here, it's sort of like the category of, you replace category of groups with the category of real vector spaces. Same thing though. It just happens to be in this case that the free vector space on a set is the same thing as kind of picking a generating set of a vector space. So in this case, if S is a basis for V, then the free vector space on S is the same thing up to isomorphism as the vector space V. So sometimes this is the notation for free vector space on a set. Or you can think about it as f of S. Same thing. Just the idea that every element of V is uniquely expressed as a linear combination over R of elements of S, the basis. And if this is unclear, please ask questions in the Discord chat or wherever. But the idea is that this while it looks fancy in this new language of Hom sets, categories, and functors, it really is at its core a familiar kind of process. Right, let's look at our next main example. So if you've done a bit of algebra, maybe you've seen something called the tensor product and these Hom functors. So the next example is that the tensor product is left adjoint to the Hom functor. Now, this is still pretty imprecise, so what we're going to do, again, is specialize to the category of real vector spaces. But this really works over any kind of category of modules over a ring. So this works for suitably nice real, something called an abelian category. And also in more general contexts, many more general contexts. Hom and tensor are very ubiquitous ideas. Right. So what this means is, in the category of vector spaces, so let's say I have 3 vector spaces, let's say V, W, and maybe U, fancy U, be 3 R vector spaces. Now, this adjunction says the following. It says that there's a natural isomorphism from V tensor W to U with V to W to U here. Now, this is a very nice category, the category of vector spaces, and in particular, V tensor W is the same thing as W tensor V. So if you wanted to, you could also say it's equally valid to write this. And I'll show you why in just a second with a nice example. Oops, sorry, it should be V. Let's pick a specific case. Let's say we are in Rn. Let's say on Rn, Euclidean space, you could pick R2, you could pick R3, whatever's comfortable for you. And our linear map will be the standard dot product. So the dot product is a morphism from, it's a linear map from Rn cross Rn to R, right? It takes 2 n tuples and sends them to this sum here. In reality, maybe I'll write it like, a dot. So if these are x and y, we write this usually as x dot y. So you can write it as a function from Rn cross Rn, but it also, by linearity, it passes through the tensor product. And so this is actually a linear map from the tensor product of Rn cross Rn to R. So you can think this determines a linear function in this set. Well, what this isomorphism is saying is that you can regard this differently. You can write it like this. Rn to Rn to R. And let's see what happens to our dot product. So the dot product looks like we send x comma y to x dot y, right? Under this isomorphism, this whole function is sent to the following. So for each vector x in Rn, we're going to send that to the linear functional y goes to the dot product of x and y. If you do any kind of functional programming, sometimes this is called like currying variables, I believe. I'm not really an expert in functional programming, but I've seen this moved around a lot. Currying variables, or curry a variable. So someone who knows a little bit more functional programming disagrees, please let me know, and I'll like to correct it. But this is supposed to be also a somewhat familiar topic in that context. So that's all this isomorphism is saying, is that these are sort of complementary ideas, that maps out of a tensor product are the same thing as you can fix one of the variables and then in the other variable you treat it as a function. And we can keep going on there, The tensor product and Hom and the free forgetful adjunctions are sort of canonical first examples of adjunctions. So these are your, like free forgetful and Hom tensor are canonical first examples. These are by no means the only important examples. And there's a fun kind of set of jokes between whether or not something's canonical or natural. Canonical has no kind of established meaning. Canonical just means that you like it a lot. But you'll come across adjunctions, say, these pop up in, say, the kind of the foundation of algebraic geometry. These are fundamental in algebraic geometry. Representation theory, algebraic topology. Etc. You can think about, there's a way of phrasing the universal and existential quantifiers as adjoint pairs in certain contexts. Maybe certain like poset categories. Right, they are adjoints in a certain suitable context. You can realize integration on manifolds is coming from an adjoint relationship, describing Poincare duality from algebraic topology. Maybe like integration on manifolds. Poincare duality. These are all kind of adjunctions. Once you have the language, you start seeing them over and over again for any kind of type of question where you ask for the most efficient solution by some formulaic process. There's always an adjoint pair lurking in the background. And they satisfy some nice properties. In addition to just existing and knowing the phenomenon, you have some kind of important results. So the first one I'm going to say, I'm not going to prove either of these. I'm just sort of giving you the taste so we can look later together at some point. Theorem. So right adjoints preserve limits. Left adjoints preserve colimits. This is not super hard to prove. Kind of a nice little idea. You can prove the first one, and then the second one follows just by taking like the opposite category of the whole idea, the whole proof. Preserving limits and preserving colimits. So let's say we have the first one, and we have our functor G before. So we have an adjoint pair F and G. What does it mean to preserve limits? So we talked about limits and colimits in the previous lectures. We've talked about universal properties. So limits are things that kind of correspond to terminal objects, and colimits correspond to initial objects. Right? And so what we want to do is say that if I have any kind of limit in the category, say D, like D sub I, then there's a natural isomorphism in this way. Here. You can kind of think about this as being continuous for a functor. This is sort of a continuous property. Likewise, left adjoints preserving colimits, you think about it as like sometimes you call these co-continuous. And we have a converse to this, right? So right adjoints preserve limits. Is it ever the case that a functor which preserves limits is a right adjoint? And this is addressed by the adjoint functor theorem. Which says the following. Well, very loosely, it says a functor which preserves limits is a right adjoint under some conditions. And so, if it is a right adjoint, it has a left adjoint. That's sort of how this works. So let's be more specific. So let R from D to C be a functor. And I'm going to assume that D and C have all small limits. So I can take limits with impunity in both C and D, provided that I only ever index over a small category. And I'm going to assume that R is continuous, that it preserves limits. Okay. Then R has a left adjoint if and only if a certain condition is held or satisfied. Sorry. Then R has a left adjoint L from C to D if and only if the following conditions is satisfied. So for all x in C, the functor from from C x to, so this is a functor from the opposite category of D to the category of sets is representable. Okay. What does that mean? What is this doing? So I'm not going to go over the proof of this, and I'm going to lay some breadcrumbs for you guys as the one exercise for this section to kind of investigate and talk about with me in about a week. So it's a kind of thing where this has many different formulations. So there, me right here, that there are many formulations. So this is sometimes called the general adjoint functor theorem. There's also the special adjoint functor theorem. There's the classical version of the special adjoint functor theorem, Freyd's adjoint functor theorem. There are many different ones, but the core idea is always this: the existence of a left adjoint to a given functor. So what I want you guys to do here is look at this condition here. I want you to tell me in the Discord chat in your own words what this condition is doing. Unpack this definition. Unpack the assumptions. What is this constraint trying to tell us? So I'll also give you some keywords to look up. Sometimes this is called the solution set criterion. Or solution set condition. So I want you guys to research, this definition here. I want you to understand and try to unpack what this constraint is saying. And then when we do like the problem session for this lecture, we're going to talk in more detail about specifically what these conditions are and how to think about this constraint and how it really represents at its core solving a simultaneous family of universal properties. So this is your sole exercise here. So I know that this isn't too much kind of dialogue for this section, and that's because there's a balance between kind of giving you just the taste, giving you the main examples, and kind of letting you loose and explore this world now. So I'll see you guys in a week in our live session. We can talk about this condition. All right. Thanks. Bye.